All right, good morning, grade 12s. Today, we are going to talk about the conservation of energy. So if you haven't caught up in the past couple lessons, we've been focusing on energy now. In particular, we talked about kinetic energy, which is the energy due to movement. And then we talked about potential energy and more specifically, gravitational potential energy, which is just the energy stored within an object due to a height that it's being carried at. Meaning that it can have the potential to move. So those are the two that we've talked about. If you haven't done those notes yet, you can just go backwards and find them on the YouTube channel. If you have and you're all caught up and you've done the practice problems, let's move on. So today we're going to talk about how to combine those two energies into a single question, into a single scenario. But before we do that, we're going to do our question of the day. So it's April 21st today. And April 21st, from what I saw online, is a good one. It's Bulldogs Are Beautiful Day today. So our question's about a bulldog. We are going to do a review on gravitational potential energy. So a 23 kilogram bulldog is lying on a table, which is 0.3 meters above the ground. How much potential energy is stored within the dog? So how much potential energy is stored within that dog that's on the table 0.3 meters above the ground? You can pause the video now and apply our gravitational potential energy formula to this question, solve it, and we can move on. So you can pause the video and you are probably finished the question now. So I'll show you the answer. The answer for this, if I can get my mouse here, is you've got the mass of 23, the gravitational acceleration is 9.8, and the height is 0.3. So you multiply all of those together, mgh, and you should get, using sig figs, 68 joules for the potential energy stored within the bulldog lying on the table. All right, so let's then move on to our actual notes for today. So like I said, today we're going to be doing notes on the conservation of energy, the law of conservation of energy. Well, hold on, I need to make this full screen. There we go. Oh, and I got rid of that. Perfect. Bear with me here. All right, let's make this full screen. There we go. Okay. And share that window. All right. Got a new setup today, so just getting it set up properly here. There we go. Okay, so the law of conservation of energy. So we talk about something in this class called mechanical energy. And whenever I mention mechanical energy, I want you to know that what I mean by that is the total energy of an object. So it doesn't necessarily specifically have to be kinetic energy or gravitational potential energy. It is the total energy, all of the energies acting on an object or stored within an object at a given time. The mechanical energy can be calculated by adding up all of the energy provided to an object by all of the different sources. Now, in our case, generally, we're just going to be dealing with potential and kinetic energy, the two that we've already covered, but we are going to cover some others. We'll talk about spring energy as well. So that could find its way into a question as well, but we'll cross that bridge later. So for right now, we'll just look at potential and kinetic energy. To calculate the total energy of an object, we just have to sum those up. So we take the potential energy, we take the kinetic energy, and we just find the sum of. Now, this follows a law which is similar to a couple laws that we've already seen in this course, particularly the law of conservation of momentum. Now, the key here to this law is that energy cannot be created or destroyed. So you can never, ever create or destroy energy. You can only move it from one form to another. So it can only be changed from one form to another. Let's take a look at an example for that. If you're on a snowboard hill, for example, and you're at the top of the hill and you're at rest, This would mean that if you're at rest, you would have, if you're at rest, you would have no kinetic energy, right? Because you're not moving. But you're at the top of the hill. So you're up at a certain height with the potential to start moving. That means that the only energy you have within you is potential energy, what we would call gravitational potential energy. Now, as you snowboard down the hill, your potential energy decreases because you're making your way down closer to the part of the hill that has no slope. Okay? You're actually losing that height. So as you go down the hill, your potential energy decreases. But what's going on as you go down the hill is you're increasing your speed. And therefore, you're not losing potential energy. Potential energy is just being converted into kinetic energy. So as your potential energy decreases, your kinetic energy increases because you're picking up speed. Once you reach the bottom of the hill, you're going to have no more potential energy. There's going to be no more slope for you to continue to go down. And your height, relative height, I mean, comparatively to the hill, is going to be zero. So therefore, all of your potential energy is going to be gone, and you'll only have kinetic energy left. So what we basically had there was a successful transfer of energy from potential to kinetic. Now, in real life, this does not work so perfectly, okay? I will post a link to a little simulation that you can mess around with, and it's on that same website that I had shown you guys a couple times, phet.org. And basically, it's going to show you that in our little physics world where we do everything on paper, we don't lose any energy in this process. But in real life, we obviously are going to lose energy due to the friction between our snowboard and the snow that we're snowboarding on. And what this ends up doing is converting some of this energy into heat, which is known as thermal energy. So that's the energy that we lose due to friction because we're converting, we're not just losing it, we're not destroying energy, we're converting it into thermal energy. We're creating heat between the snowboard and the snow. So we don't have to worry about that for our scenarios right now. We're not going to worry about losing energy due to heat. We're just going to assume that we're in, like I said, our little physics world here where we don't lose energy for the time being. What that means is that we've got a conservation of energy going on. So there's a conservation of mechanical energy. And what it means then is that the mechanical energy, remember, mechanical just means total. Mechanical energy before the event is going to be equal to the mechanical energy after the event. The mechanical energy at the top of the snowboard hill is equal to the mechanical energy at the bottom of the snowboard hill. And it can be written as follows. We don't have to use any sort of subscript or prefix. We just have the letter E. And I'm going to use E1 to represent energy before and E2 to represent energy after. So E1 is equal to E2. Now, at any given point, remember, we have some sort of combination of kinetic and potential energy. We're going back up here and remembering when I said that at any given point to calculate the mechanical energy, we have to take the sum of the potential and kinetic energies. So what that means then is that before, our initial kinetic energy plus our initial potential energy is going to be equal to our final kinetic energy plus our final potential energy. So that's our formula that we're going to work with today, is KE1 plus PE1 is going to be equal to KE2 plus PE2. Now, there's one very important note that I have underneath here, and we're not going to explain it yet, but we're going to come back to it after we talk about the work-energy theorem. So that note states that the above, KE1 plus PE1 is equal to KE2 plus PE2. The above there was written assuming that there was no work done. And I will get back to that. I will explain what I mean by that. First, I have to introduce you to something called the work-energy theorem. What the work-energy theorem is, it's just another way of writing the conservation of mechanical energy and that formula in terms of work. Remember from our, I think it was 3 lessons ago when we were talking about work, we talked about work as being a change in energy. So we can then relate work to our, conservation of energy formula here. What we can write down is that work being I'm going to write it above here because I'm not going to have room inside of here for all of it. Work being just a change in energy. Well, let's just take one of these from up here. We remember that work is equal to the change in kinetic energy plus the change in potential energy. Now, if I want to write out, remember change, that's what the delta means there. If I want to write out that change in kinetic energy and that change in potential energy, I get then that work is equal to the final kinetic energy, KE2, minus the initial kinetic energy, KE1, plus the final potential energy, PE2, minus the initial potential energy, PE1. So all of a sudden our formula looks like W equals KE2 minus KE1 plus PE2 minus PE1. And this all just stems from the fact that work is equal to the change in energy. Now, let's take a look back up here above and assume that there was no work done. If there's no work done, let's go to our next page here and replace work with our numerical value for none, which is 0. If there's no work done, that means that work is going to be equal to 0. So rewriting our formula then, 0 is equal to the change in kinetic energy plus the change in potential energy. All of a sudden, this is starting to look familiar as to what we were doing above, is that if I rearrange this, I'm going to start to get something that looks really similar to what we had initially in the conservation of mechanical energy theory. So this theorem can be changed to show that it is equal to the conservation of mechanical energy. I just have to do some small rearranging. So what I have here is, use a different color here, 0 is equal to, remember, we'll write this out, KE2 minus KE1 plus PE2 minus PE1. And with some simple rearranging, I can see something very interesting here. What I'm going to do is I'm going to move my initial values, my KE1 and my PE1, I'm going to move them to the other side of the equal sign here. So I'm going to add them on both sides and move them over there. And what it's going to end up giving us is that KE1 plus PE1 is equal to KE2 plus PE2. And that looks extremely familiar. That is the exact formula that we wrote down here for conservation of mechanical energy when I first introduced it to you above. So what I'm saying here is that this, in order for KE1, so the initial kinetic energy plus the initial potential energy, to be equal to the final kinetic energy and the final potential energy, there has to be no work done. Okay? So if there's no work done, that means that those are going to be equal to each other. All of the energy before is going to be equal to all of the energy after. So there you have it, a little bit of a proof there for you. Now let's do some examples. So a ball with a mass of 0.25 kilograms is thrown downwards from a roof that is 18 meters high. Initially, the velocity is 16 meters per second. What velocity does it hit the ground with? So let's draw our little roof here and our person with the ball. There we go. So initially, this person is throwing it with a velocity of 16 meters per second. That's initially. So that means that we have kinetic energy at the start here. And this ball is also way up in the air, right? It's also 18 meters up in the air. So that means that there's also potential energy initially stored within that ball. So we've got a combination of kinetic energy and potential energy stored within that ball. And then once the ball is thrown, we're trying to find what velocity does it hit the ground with. So not what velocity is it right after it hits the ground, because we all know that would just be 0. It's what velocity does it have when it hits the ground. And that would be KE2. But when it hits the ground, there's no height. So we don't have a potential energy for the final. So let's write out our conservation of energy formula. The total energy before is equal to the total energy after. Let's break it down into its two parts. KE1 plus PE1 equals KE2 plus PE2. We just said that there's no PE2, there's no final potential energy because it's at 0 when it hits the ground. So now all that's left to do is replace KE and PE with their formulas that we learned in the last lessons. So KE, remember, is 1/2 mv squared. So 1/2 mv1, that's the initial velocity, squared, plus mgh. You could write mgh1, that's the height initially, equals 1/2 mv2 squared, and then obviously 0. So a really nice thing right here is I could actually ask you this question. This is similar to what some of the stuff we were doing before, where I have a mass value in every one of my terms here that's going to cancel. So you might see a problem. Here's a hint for you. You might see a problem like this with conservation of energy where I haven't given you mass. And I remember that tripped a couple people up when we were doing this in the past in our dynamics unit. So make sure that if mass is inside of every unit, that you're checking to make sure that you can actually cancel it out, because if it looks like you don't have enough information, maybe there's a cancellation that you're missing. So let's keep going. 1/2, we'll plug in our initial velocity, 16 squared, plus g, which is 9.8, times the height, which is 18, equals 1/2 times, we're trying to find V2 squared. So in order to find V2, I'm going to have to multiply. I'll do my steps right here. I'm going to have to multiply by 2 on both sides to cancel out that 1/2. And I'm going to have to take the square root to cancel out the square. So there you have it. We are going to have V2 is equal to the square root of 2 times, I'm going to do what's inside of my brackets here. So we've got 1/2 16 squared plus 9.8 times 18. And that should give us 304.4. So there we go, 304.4. And 304.4 times 2, and then under the square root. If I plug that into my calculator, I should get 24.7 meters per second. Let's take a look at our question here, and our least amount of sig figs is 2. So our final answer, I'm going to write it over here, should be V2, and I'm actually going to make it a vector because we do know that this is going to be going down. So V2 is going to be, with 2 sig figs, is going to be 25 meters per second, and I will write down. There you go. So there's our final answer. Right there, 25 meters per second down. Let's do one more problem. What upward velocity must an Olympic high jumper have in order to clear a bar set at 2 meters? Assume an upwards displacement of 1.15 meters from the jumper's center of mass. So let's draw this out. The drawing, I'm going to warn you, is not going to be to scale or anything like that. It's not going to look exactly right. But you've got the jumper right before they're going to jump. Right here. and then they are going to jump up and over a high jump bar, like so. Okay, oh, they don't have a head here. There we go. Now, although the bar is set at 2 meters, we're actually only concerned with this point from their center of mass right here. So we're only concerned with the last 1.15 meters. That's the displacement, the upwards displacement that we're looking at. So let's take a look at this in terms of our conservation of energy. So we have got what upwards velocity must an Olympic high jumper have? So we're going to be trying to find what is V1, right? What else do we need to know? Initially, because we're jumping from the ground, initially that potential energy, PE1, is going to be equal to 0. When that jumper is at their peak height, what's their velocity going to be in the y direction? 0. So that kinetic energy in the final position is also going to be 0. So this makes our formula a lot easier. When we have E1 equals E2, then we're going to have, right, KE1 plus PE1 equals KE2 plus PE2. But we just said PE1 is equal to 0, no initial height, and KE2 is equal to 0, no final velocity. So now we have a lot more straightforward setup. We have 1/2, oh, I'm using a different color here, 1/2 mv1 squared is equal to mgh, and I'm going to call it mgh. Now you'll notice in this problem, I did not tell you the mass of the Olympic high jumper. So if we didn't realize this, we would think that we don't have enough information here. But you don't need the mass because the mass is in the kinetic energy formula and it's in the potential energy formula. So you just divide by mass throughout and they both cancel. Don't ever try to cancel out masses if it does not appear in every single term, okay? Or if you have different masses. But the mass of this jumper is not going to change, therefore we can cancel them out. So now what we have is the same kind of setup as the last time. We're going to end up with the root of 2 times the value. That's just how I isolate for V1. And V1 is going to be equal to the root of 2 times G, which is 9.8, and H2, which is 1.15. That was the height that we jumped. And there you have it. So 2 times 9.8 times 1.15, and then the square root of that should give me that V1, the initial required velocity, is 4.7 meters per second. And he has to jump, or they have to jump up. Let's push forward here and just get through this last set of conservation of energy examples. There's one more, and we're going to solve it 2 ways, and we'll get the same answer for both of them. And then we're just finished with conservation of energy nicely. So let's just do them. It shouldn't take too long. They're pretty straightforward examples. A 25-kilogram girl slides down a slide at the park. The slide is 2.5 meters high, and she starts at rest at the top of the slide. At the bottom of the slide, she's on the ground and moving 1.5 meters per second. What is the work done by friction? So the first thing we're going to do is we're going to solve this question using the conservation of energy. And then we're going to solve it using the work-energy theorem. Okay, so it's going to look a little bit different than what we just did, because what we have added on here to make this a little bit trickier is friction. What is the work done by friction? So rather than just having a very straightforward scenario here where it's E1 equals E2, we're introducing friction. So we're introducing an extra amount of work that's being done. So I'm going to have to take a closer look at this here. Initially, the girl is at the top of the slide. So initially, she's at rest. So KE1 equals 0. At the bottom of the slide, she's on the ground. So PE2, the potential energy at the end, is 0. Okay, we've got a V2 of 1.5 meters per second. We've got an initial height of 2.5 meters. And we have a mass of 25 kilograms. So what is this going to look like? Well, let's write it out like this. We would have initially KE1 plus PE1 equals KE2 plus PE2. Now let's get rid of the ones that we know are equal to 0. KE1 is 0, PE2 is 0. How do I introduce friction into this problem? What is the work done by friction? Well, what friction is going to do is friction is going to be another source of change of energy within this problem. So as I have different energies in here, inside of my conservation of energy problem, I'm also going to have work acting on it. So work can be added on at the end here because it was the amount of work that I added on, or you can kind of subtract it at the beginning here because it's going to be, friction is going to be acting against our initial energy. So we're going to add work at the end here just with a W. So now we have, and the energy initially is equal to the energy finally, which is the kinetic energy, the potential energy, and the work that was done by friction as well. There was 3 things acting on that girl while she was sliding down the slide. 3 different types of energies. Now all we need to do is solve for work. So we get W is equal to, let's say, okay, so PE1 is going to be mgh1, and then all I had to do was move KE2 to the other side. So I get minus 1/2 mv2 squared. And then we'll plug in our values. So we can't cancel out the m's here. We'll write them out. 25 times 9.8 times 2.5 minus 1/2 times 25 times our V2, which is 1.5 squared. And if we do all that, work, remember, is just a scalar. I plug that all into my calculator. So 25 times 9.8 times 2.5 minus 0.5 times 25 times 1.5 squared. I should get 584 joules. Now in our question, I think our least amount, no, that's good. Yeah, 3 sig figs, perfect. So there's our final answer for the amount of work. Now that was kind of a tricky way to do it. Let's take a look at how we can do the exact same problem using the work-energy theorem this time. So this time we're going to use that second formula that we learned, the work-energy theorem. And this one looked like this. It was the work is equal to the change in kinetic energy plus the change in potential energy. Remember, work is just defined as the change in energy. What that ends up giving us is KE2 minus KE1 plus PE2 minus PE1. Remember, our KE1 was equal to 0 and our PE2 was equal to 0. So now we just end up with the same idea here, 1/2 mv2 squared minus mgh. And if I plug my values in, I should get 1/2 25 times 1.5 squared minus 25 times 9.8 times 2.5. And my work will be equal to, if I do all of this, I should get the same answer, although I remember my setup here, I'm remembering from the last time I taught this, my setup here in this scenario versus the last scenario. The last scenario, I looked at it as on how much work was done by friction, and in this scenario, it actually shows us how much energy was lost due to friction, and we end up getting a negative answer for that reason. So that's the only difference between those two ways. That's kind of why we don't really look at it. We only look at it as a scalar because you can kind of explain it in a couple different ways. So therefore, here I'm just going to explain, I'm going to say energy was lost, which makes sense. We lose energy due to friction. So that is it for our lesson for today. It was a bit of a longer one, but that way we don't have to split it up into two different lessons. So I will talk to you later. Let me know if you have any questions. Now that we're done this, you can just work on the practice problems that are on the next page, or on the page 6.1, I think, in your homework booklet. And there is quite a few problems for you to do. I think there's 9. So good luck with those. And yeah, email me with any questions you have. We'll have another live session on Thursday around the same time as we did the last time we did it, for you to ask questions as well. Okay, we'll talk to you.